Good afternoon, everyone. I would like to thank the organizers for giving me this opportunity to present my work here. I will be talking about entanglement behavior in lattice bosons with cavity-mediated long-range interactions. It's based on this work. And this funding was done by DFG, Guided and Aquas when I was a postdoctoral fellow affiliated with UDS and ICTP. And currently I am in NIT Rourkela and my funding is, so my research is funded by DST Inspire faculty fellowship. So the motivation of this work is we see that quantum entanglement is the main ingredient of quantum speed up in quantum computers. However, due to numerical costing, it's very difficult to study the behavior of entanglement entropy in two-dimensional systems, and let alone the systems that has long range interactions. So for this we targeted this two-dimensional long range Bose-Hubbard model, which exhibits new phases of matter other than like the Mott insulated and superfluid phases that exist in a Bose-Hubbard Hamiltonian because of the short range interactions. There are also new phases in this new exotic phases in this model referred to as supersolid and charge density wave. And what we want to do is we want to characterize the scaling of entanglement entropy as a competition between this short range and global range interactions. So I will talk about what I mean by global range interactions, and I will also talk about these exotic phases, namely the supersolid and charge density wave, what they look like. So to begin with, I introduce first the model Hamiltonian in the two dimension, and it is based on this experiment in ETH Zurich. So the idea is, if you look at this figure here, the idea is you take a Bose-Hubbard model, which is a lattice model, which a two-dimensional lattice, which has bosons that can hop on it in the nearest neighbor given by strength T. So if you look at this figure, the red dots are the dots that is the Bose-Hubbard model I am talking about, or the two-dimensional lattice where bosons can hop. And then if you see, these are the gray photons that are coming. So the idea is you place this two-dimensional lattice inside a cavity system, where with cavity I loosely just mean very good mirrors. You put your two-dimensional system in very good mirrors, and then you start to pump it. That is, you shine a good laser on it. And when the photons bounce off the atom into one of the cavity modes, you get these like blue standing waves, or you get the new patterns in the Hamiltonian that gives rise to long range interaction. So if you consider this red part here, HBH is the Bose-Hubbard Hamiltonian, which were these red spots shown here in the figure, that represents, for example, the first part, the hopping to the nearest neighbor of the bosons on this two-dimensional lattice. Whereas there is this on-site interaction, which is the price or the energy price that you pay when two bosons are on the same site, because these are bosons, they can do that. Whereas the last term is the chemical potential that takes care of the fact that how many particles enter or leave your system. However, these blue lines that you see, or the new Hamiltonian that comes up in this picture is the Hamiltonian that comes because of the long range interaction. As I said, this long range interactions comes because of these photons that you pump your cavity with. So there is a different part of this Hamiltonian of the photons that gives rise to a potential, which I have removed from here. But this is the effective Hamiltonian that you get in a limit where you have now adiabatically eliminated the cavity. So the idea is we use this Hamiltonian, and loosely I will tell you how you can visualize different phases out of this Hamiltonian, these exotic phases that I was talking about, and then we will move to the further discussion of how we will look at the entanglement entropy. So just mainly for the students, so if this is your Hamiltonian, and if you consider different terms, you can visualize different phases of it, just like as a cartoon picture. So the idea is, if you look at this U0 term here, which is the on-site interaction, you see that it does not provide any hopping, and this can be related to a phase called Mi, or the Mott insulator phase, where your bosons or the particles are stuck to the local minima, and that's why called an insulating phase. However, if you have this term which is underlined by the red color, the hopping term, if it dominates in the system, then your particles are free to hop from I to j sites, and these are nearest neighbor sites. But if T is so large, it will appear that your particle is hopping from one side to the other, so that it appears that it's something called superfluid or a phase that has a long range coherence. So you cannot like pinpoint the particle at the minima. However, because of this green part here, the long range part, when it comes to the system, along with this U0 interaction, like the price that you have already paid that two particles can stay on one side, you can imagine a phase, namely the charge density wave or CDW, where you'll have an even odd imbalance in the system. As you also see from this part of the Hamiltonian here, ULR is the long range interaction strength. However, this strength comes with these operators where you have where you write the occupation as a disbalance between or a subtraction between the occupation in the even site and occupation in the odd site. So N are the number operators, whereas this Bi, Bj daggers are the annihilation and creation operators respectively. So in that case, you will always have a phase that has an even odd imbalance, and these are also insulating phases, but they will always come up with so something like which favors, for example, the even side occupation more than the odd side. So it can be 1 0 1 0 like shown here, or 2 0 or 2 1 and similar phases. However, imagine that along with this long range interaction part, now you have a large T value or the hopping, and now this charge density wave structure can hop around in the system in a very crude way. So this is something that we are referring to as a super solid phase, where you have a density modulation, and by density modulation I mean that even odd imbalance in the system, but then there is also a long range coherence in the system, and this is what we are referring to as a super solid phase. Now the point is, as I said before, numerically this is, I mean if we want to calculate the entanglement entropy of this long range Hamiltonian, numerically it would be challenging. So first of all, we go to something called a mean field analysis. Mean field analysis, for the students, as the name considered, it is replacing these interaction terms, or like the terms that are difficult to solve, for example, replacing this by an average of the neighboring fields. So what we are doing is we are going to replace these terms that come as a pair and replace it with the average from the neighboring sites. So in that case, what we'll do, we'll actually try to break the ij, or like the site dependence of the Hamiltonian, try to bring it to a single site Hamiltonian. That is numerically very easy to solve. So we'll define, for this we'll define a superfluid order parameter, say phi I, and then from the long range part also we want to do that, because this part is comes with a square, so you understand that it's kind of an ij, so it's an all-to-all interaction term. So it's like a global range potential that we have in the system, and we also try to then give a mean field to it, and we defined a parameter theta here, which we refer to as a long range order parameter. So we have two parameters in the Hamiltonian, one the superfluid order parameter, another the long range order parameter theta. And if you don't understand this mean field at the moment, I would be very happy to, like, you can reach out to me, and I would be very happy to answer questions now or later, whenever you like. But with this mean field, as I said, the idea is that you write your interacting Hamiltonian in terms of a single site Hamiltonian. And because of the form of the long range interaction that we have in the system, you will always, the lattice would now look like a lattice that has a Hamiltonian or the mean field Hamiltonian for the even sites or the odd sites. So because you have an even odd imbalance, so from the charge density wave picture you can figure out that the even sites would have different occupation than the odd sites. With this in mind, the idea is these two order parameters, if you try to put in a table, you can quantify all the phases in the mean field picture from these two parameters. For example, in Mott insulator phase, you expect the values of these two order parameters to be 0. However, in phases like charge density wave phase, you have this phi to be 0, the superfluid order parameter, but it comes because of the long range interaction, and therefore theta is not equal to 0. So with this in mind, and knowing the idea of how so at the end numerically they would come out to be number, how these numbers would look like or how these order parameters would look like, you can quantify the whole phase diagram of the system. But the problem is this is a single site Hamiltonian, and what we said that we want to look at the entanglement entropy. And entanglement entropy, as the name suggests, is how your part of the system is entangled to the other part of the system. So now we cannot stop here at the mean field level and calculate entanglement entropy from here, because it is a single site Hamiltonian, be it for even site or the odd site. So what we do is we use this technique of the slave boson approach. The idea here is similar to, like very crudely similar to a Taylor series expansion, where if you know the minimum value of the parameter and you start to expand a function about the minimum value, the very first value is or the very first value of the function is the function at this value x naught, if x naught is your minimum value. The first order term is 0 if it is a minima, and the second order term survives, and you can go on to the higher orders. So we do a similar thing. We take these, we find out the mean field solutions. We call that these are the energy minimum solution, and we take the original Hamiltonian and rotate it to these new mean field bases, and we start to expand about the mean field ground state. And with this in mind, by doing some calculations, I will not go into the details, but like I can if you ask questions, and we can also discuss it after the talk if you want. But the idea is you start to expand about, so these operators that I have defined on above the mean field ground state, and keep the expansion up to the quadratic Hamiltonian. Similar to the picture of Taylor series expansion, the first order term would be the mean field Hamiltonian. Sorry, the 0th order term would be the mean field Hamiltonian. The first order term would be 0. This is a very good numerical check also, and the second order term leads to a quadratic Hamiltonian, and we stop at the quadratic Hamiltonian at the moment. Now this quadratic Hamiltonian will have a form like this. That means now I have up to the mean field order kept the interaction between the I and j parts of the or like the interaction between the different sites in the Hamiltonian. And with this picture in mind, we can now calculate the entanglement entropy. Now this is still an expansion above the mean field solution, so the results are not exact, and these are kind of a mean field results. However, mean field starts to get better and better as you move to a higher dimension. So we are considering a two-dimensional system. It starts to get also better if you have a long range interaction in the system, and we have a global range interaction in the system, because you can imagine if you have more and more average field coming into one single point, the calculations will start to get better and better results, and you have higher values of the averages that you are adding. So in our case also, we thought that it would be a good approximation, and it is known. If you don't know, if like the students don't know, then take my word for it. For a quadratic Hamiltonian, it's very easy to calculate entanglement entropy, because it depends on these two quantities that you are calculating, referred to as correlations. So the idea is this: consider this to be my square lattice. I divide it into two parts, A and B, so A being green and B being the pink one. So you see, the idea is I will form a correlation matrix for the subsystem A, and when I am forming this correlation matrix for the subsystem A, the information that it is for a subsystem A is stored in this I and J. Here I and J will belong to only the points in this green part or the A part of the Hamiltonian. However, the average is taken over the whole ground state or the whole system. So this particular matrix that you will form will have the information about the entanglement between the A and B parts of the system, and from here you can calculate the entanglement entropy. And we ask the question, what is the behavior of entanglement entropy or its scaling when you are competing between this short range interaction hopping or the long range interaction u long range that you have in this system. So this is the solution that we obtain, and there are many information here, so let me like take you step by step. This was the original Hamiltonian, however this is not the Hamiltonian at the end. What we are doing is we are doing a mean field expansion and keeping up to a quadratic order. But what we see is for example for a long range term being equal to 0.3, we see a phase diagram or the entanglement entropy phase diagram of T versus mu, where T is hopping, mu is chemical potential. We see that there are phases like charge density wave, supersolid and superfluid for a fixed value of mu, and as you keep on increasing mu, you get trivial phases like the phases for occurring from the short range interactions like or the short range hopping are Mott insulator and superfluid. Whereas as you increase the U long range to a larger strength, say 0.6, we start to see that we lose the Mott insulator phase altogether, and these Mott insulator phases are replaced by the corresponding charge density wave, followed by the supersolid and then the superfluid phase as you keep on increasing your hopping strength T. Now the main point is what we observe here is the behavior of the entanglement entropy at different phase transitions points. For example, the behavior of entanglement entropy at these peaks of charge density wave to supersolid transition, and the behavior of entanglement entropy from supersolid to superfluid. With this in mind, we start to target 3 different types of phase transitions in this system. One, the type 1 transition, where we have the charge density wave to supersolid transition but at the fixed densities, and these are referred to as the continuous O2 transition. These are similar to Mott insulator to superfluid transition at fixed density. So like the mu doesn't come to picture here, we have kept the density fixed, and we can vary mu such that the density is fixed here. So this is referred to as the continuous O2 transition. Then there is this second transition which is at a fixed mu but varying density, and this is commensurate incommensurate transition. This is from the charge density wave to supersolid transition or Mott insulator to superfluid transition but at a different mu value, a fixed mu value say. So the idea here is both of them are insulating to non-insulating phase transitions, but they both belong to different universality classes. However, the third transition is the supersolid to superfluid transition, which is the transition between the two compressible phases, and this will refer to as the continuous Z2 transition. So we will consider or we will target only type 1 and type 3 phase transitions. Why? Because they will actually probe the short range versus the behavior of entanglement entropy or scaling of entanglement entropy for short range versus the long range transition. So if we plot for fixed density the entanglement entropy, for example for the fixed density rho is equal to 1, which is going from Mott insulator to superfluid shown here, we see that there is a peak of the entanglement entropy at 0.1, which we can also see as a bright spot here. Similarly, we see a peak from charge density wave to supersolid phase transition at fixed density 0.5. Given by 0.1 here, but as soon as we go from supersolid to superfluid phase, there is also a very small peak here happening at the transition of supersolid to superfluid. We can also see from here that the whole phase boundary from supersolid to superfluid has some kind of peak structure. So we ask the question that why do we have peaks at these transitions, be it transition from an insulating phase to a non-insulating phase, or be it the transition from one supersolid, so two compressible phases. And then we ask another question, what should be the scaling of entanglement entropy for these two peaks? So to answer our first question that why do we have peak at these transitions, we explore the physical and entanglement spectrum of the Hamiltonian that we have at hand. So what we see is if we look at the physical spectrum like targeting this square here like for example the type 1 phase transition, which is the transition from an insulating phase to a non-insulating phase. Targeting these transitions here, if we look at the physical spectrum, that is if I have the Hamiltonian, I diagonalize it and I look at the energy versus k for the Hamiltonian that I have at hand, I see that the ground and the first excited state both linearly go to 0 in both the cases, be it fixed density 1 or density 0.5. Similar thing if I want to observe in the entanglement spectrum, we see, so entanglement spectrum is also something that you obtain from the correlation matrix that I showed you a few slides back. And here also we see that right at ky is equal to 0, many higher entanglement modes starts to contribute and starts to soften, and this is the reason that because of the contributions from higher and higher entanglement modes that come into picture or soften or goes to 0 at this ky value, this leads to a higher peak in the entanglement entropy. So therefore, the type 1 transition, which in the physical spectrum is related to the softening of not just the first excited state but the second excited state, that is not just the Higgs stone but also the Goldstone mode. Similar thing happens in the entanglement spectrum, and similar Higgs-like mode soften in the system, not just the Goldstone mode, and this leads to a higher or a peak in the entanglement entropy for the type 1 phase transition. This was already seen in this paper by Freroth and Rochilde for the Mott insulated superfluid phase transition. However, we ask the next question, what happens at this point where we see a transition from the type 3 transition, where we see a transition from supersolid to superfluid phase. And this is something that was never explored before, and for this we started to see the behavior again of the physical spectrum, where we see that okay, if we go from a supersolid phase to the boundary and to the superfluid phase, we see that the first excited state does not soften like it did previously. However, there is just one single mode, or like it is called the Roton mode. It starts to go down and it becomes gapless right at the transition, and then it starts to again have a gap as you move in the superfluid phase. And similar contribution comes in the entanglement entropy, or the similar contribution comes in the entanglement spectrum for this one single mode that softens right at the critical point, and it is this one single mode that gives rise to this peak behavior at this transition from supersolid to superfluid. This mode is called a Roton mode, and it is an artifact of the global range interaction that is present in the system. So the idea is this type 3, if we want to talk about this type 3 phase transition, and I consider just k is equal to 0 value or k is equal to pi value, it linearly goes to 0 at the critical point of the transition, and then it becomes non-zero. It is the center plot with the black circles are actually the black circles are actually the entanglement spectrum at just this lambda Roton value, the mode corresponding to the Roton mode in the physical spectrum, whereas the red circles correspond to the physical k is equal to 0 or k is equal to pi when you fold your Brillouin zone, k is equal to pi mode in the physical spectrum. And you see, it is not just the artifact of the fixed density transition if you go from one incompressible phase to the other. It is also you see it at a fixed mu value. So the point is, this transition or this mode occurs, as I said, for the whole boundary of the system from supersolid to superfluid phase. So this Roton mode softens at supersolid phase boundary, and it is because of the long range interaction that is playing a role. It has also been seen experimentally, so this is known for long range or global range interacting systems, that one such mode would appear and may lead to behavior in the, it was not known that it may lead to a behavior of the enhanced entanglement entropy, but this is what we observe here. Now next question is, what would be the scaling of entanglement entropy considering that there is this one single mode that is contributing? And therefore we look at the fitting function, which is the usual fitting function for the entanglement entropy, that there is this linear part and the logarithmic part followed by some constant. And then we see that, and we took this because we know from the previous works that if there are number of Goldstone modes in the system present, for example, some system like this, then there is a log correction, and the coefficient of the log would depend on the number of Goldstone modes in the system. In our case, the number of Goldstone mode is 1. So we start to now look at the behavior of A. So this is A and this red part is B. So we start to look at the behavior of the A and B when we go across the fixed density or a fixed mu transition to explore what would be the behavior of A or B when you have a long range term in the system. And what we see is as expected, because the number of Goldstone mode in the system is 1, we expect in the super solid and super fluid transition the B scaling, the coefficient of the log to scale as 0.5, we see it. However, right at the transition of the super solid super fluid, because of the Roton mode, it seems that there is another contribution coming into picture. Since it's not an exact numerical calculation, we cannot say like for sure, but we see that this value changes because of this one single Roton mode, or k is equal to 0 mode that comes into picture because of the long range interaction. So we see the entanglement entropy scaling changes. When there are short range terms playing into the action, you see the usual correction to the log to be half. However, when there are long range interactions playing into picture, it seems like it acts as a new ng value. It adds to the different value of the coefficient of the log, and then this scaling changes. So with this in mind, we to conclude, we looked at the entanglement entropy for the phases like charge density wave and super solid, and we saw that there is a log term that originates from a singular vanishing Roton gap in the system. So this is like the takeaway, and outlook would be to see the behavior of entanglement entropy not in just clean 1 0 1 0 super solid phases, but rather in incommensurate lattice kind of systems. So where you have phases like Bose glass or spin glass. So with this, I want to thank you. Also, this is the group that contributed to this work, including Tomasho Roshilde. And 30 minutes this advertisement. This is my group in NIT Rourkela. We are working on quantum computation, quantum information, and Bose-Hubbard models, long range Bose-Hubbard models. Thank you. I have thank you. Thank you.
So in the excitation spectrum, how do you identify this Goldstone Higgs?
So it's a very good question. So you cannot just pinpoint and say, but see, the idea is as you move from, for example, you look at the entanglement spectrum here. So in the excitation spectrum of the entanglement or the physical spectrum? Okay. In the physical, it's very easy to see. Like you see, so for 2D, it looks like a mess. But if say I like want to see it for a one-dimensional system, you'll see that if you diagonalize the Hamiltonian for a k for different k values, and you plot this ground state and the first excited state energy with respect to the k for this Hamiltonian that depends on k. So you plot Ek versus k, and you'll see that it linearly goes to 0, and then like the ground state solution. For this transition, like at the critical boundary, it's 0 for both the ground and the first excited state, so the Goldstone mode and the Higgs mode. But this happens right at this fixed density transition. If you move away from this fixed density transition, that's why I said there are two, so there is this transition also. Here the first excited state would not linearly go to 0. So there would be like only the ground state would go to linearly go to 0. So the next first excited state would not be. So you have to be very careful that it is not a fixed mu transition where both the ground and first excited state goes to 0. It's a fixed density transition right at the fixed density. So these are different universality classes 1 and 2.
So I was just having a very naive question. So by looking at this plot, you are saying that there are different these regimes of phases. So just by looking at this entanglement entropy plot, how are you saying that?
Very good point. We did not do that. So I hid that information. Just by looking at entanglement entropy, it's impossible to differentiate between charge density wave, Mott insulator. What we do is look at this for the whole like for mu L fixed value and mu, so U L fixed value, mu versus T. We look at how these are behaving, and from this table we pinpoint all the phases, and then the next step would be to look at the entanglement entropy, and these labeling are done solely on the basis of the order parameters and not the entanglement entropy.
Okay, so let's thank Dr. Sharma.
Thank you. Thank you.